Now we're going to look at the crossed aldol reaction. In the crossed aldol, we're reacting an aldehyde or ketone with another aldehyde or ketone that's different, but doesn't have an alpha hydrogen. We get a similar kind of product to what we got with the aldol. Let me show you an example. And here is our example here. And I'm going to go ahead and show you what happens. In the first step, the OH minus will remove the H from the one that has the alpha hydrogen, and that will give us this anion. And you can see that we've got benzene rings here, so there's no alpha hydrogen on this one. No doubt about where the alpha hydrogens are going to be removed from. Alright, so we get the joining of the two groups here. The removal of a proton. From water. And then we can have OH minus come in again, remove this proton, and then form the double bond, remove the other OH. Now you'll remember in the aldol, I said that there were many reasons that we got this double bond here, and conjugation was one of those reasons with the C double bond O. But if we've got these two benzene rings here, then we've got even more conjugation going on, also a whole lot more substitution going on. So this is a very easy double bond to form in this instance. Now you also remember in the previous one I used squiggly lines to indicate the possibility of cis and trans isomerism. And what I had said there was that as long as you've got two different groups attached to each carbon from the double bond, here we've got two different groups attached to the carbon here, but down on this carbon we've got the same group attached. Therefore, cis and trans isomerism is not possible. Another way you can look at this is to say, well, if I switched the phenyl with the phenyl, would I get a different compound? And the answer is no. So no cis and trans isomerism is possible. That's why I have not included squiggly lines on this structure. Now looking at this, remember how I said that we could use a pattern to figure out the product? I'll apply that pattern to the crossed aldol as well. There's no doubt about where the alpha hydrogens are going to come from. It has to come from the one that has alpha hydrogens. And you can see we join those together and we will end up with the product that we came up with from the mechanism. Alright, with the loss of water. Alright, so that's what we're going to, that's what we got. The importance of making sure that one of these does not have alpha hydrogens. So what I want to do is go through and show you an example of what would happen if we decided to use two different things that had alpha hydrogens with them. Now I'm not going to do the mechanisms for these, I'll just follow the pattern that I've been talking about. So an example would be something like this. Let's say we use this aldehyde, and we used, say this aldehyde. Right, so what we've got here are two compounds, and they both have alpha hydrogens. So the kinds of compounds we could get, since we have two possibilities for the alpha hydrogens, we could use these alpha hydrogens and use the other compound and follow that same pattern I've been talking about. join them together, and this would be one product. And since we're going to end up with two different groups attached to each carbon from the double bond, then we're going to have cis and trans isomerism possible in this instance. So that's going to be one of the products, or if you like, two of the products if you're counting the fact that cis and trans. And let's look at how we might get the other one. So what I would do is use the alpha hydrogens from the second compound and react that with the carbonyl group. And join them together, and the compound we'd end up with would be this one. And again, we have two different groups attached to each carbon from the double bond, so cis and trans isomerism would be possible, and this would be the second product. Now what I want to convince you of here is that what we have are two different compounds, actually two different sets of cis and trans isomers. This and this are definitely different, and this is happening because we have two compounds that have alpha hydrogen. So if you're going to do a cross aldol, you're definitely going to have to use compounds that have one compound that has an alpha hydrogen and one compound that does not have alpha hydrogens. Just let me make an experimental note about the crossed aldol process. What we would probably do is we would need to find a way to manage this so that we never had the opportunity for this to react with itself. So that would mean arranging your apparatus in this way. We use a dual neck flask, and in here you would put the one that didn't have the alpha hydrogens, and you'd put that in sodium hydroxide. Now the sodium hydroxide won't react with this one because it doesn't have any alpha hydrogens. And now what we could do is we could very slowly add the aldehyde through the top here, and we would do so dropwise. And what would happen is there'd be a very large concentration of this, and we'd have the sodium hydroxide. So as soon as the anion formed, it would have no choice but just to react with this, because this is being added dropwise, and it's pretty much just reacting as it hits the reaction solution. So we never build up enough of a concentration of the aldehyde for it to create a problem and react with itself in solution.